Welcome everyone, my name is Christian Williams and I'm going to present you our work on deep Felsenswap segmentations for superpixel-based object proposal refinement. This is joint work with Simone Frimtrop, and this paper was previously accepted by the Image and Vision Computing Journal. The problem that we want to tackle is object proposal generation. That means we want to localize and segment all objects in an image. This is a class-agnostic procedure, thus we are not bound to a specific set of classes that we've seen in training, but we want to localize objects of all classes, and we do not want to classify them. Typically, in our case, we generate pixel-precise segmentation masks as proposals. This is something you can see in the top right corner. The green object proposal covers the airplane. A typical problem in object proposal generation is that, as you can see in the top right corner, the proposals are rather coarse. This is usually due to the subsampling in modern CNN-based systems, reducing the resolution to, for instance, only 10 by 10 pixels for segmentation. Note also that we usually have not only one or two proposals per image, but usually hundreds or thousands of proposals showing different objects or object parts. Hence, typical methods for refining initial segmentations like conditional random field can't be applied to hundreds or thousands of proposals per image. Thus, we propose a new idea using superpixels, which capture fine details of objects, and combine the coarse proposals, as you can see it in the top right, with fine-grained superpixels, and classify each superpixel as foreground or background per proposal, generating the refined results as you can see them in the bottom right corner. A typical problem when using superpixel segmentations in CNNs is that superpixel segmentations don't have the lattice structure necessary for CNN computation. This is also a reason why many superpixel segmentation algorithms still using classic methods and don't utilize CNNs. Hence, typical problems of superpixel segmentations are that most of those segmentation methods rely on low-level features, for instance, color. Additionally, the merging or cutting of pixels or superpixels is based on rather simple heuristics. For instance, the well-known Felsenswap-Puttenlocher algorithm generates superpixel segmentations based only on RGB color differences of adjacent pixels and greedily merges those pixels to form superpixels. A result of this algorithm can be seen in the top right corner here, with 3 or 4 marked arrows with the red circles. A typical problem, as you can see in this image, is that objects consist of multiple colors or complex textures. This, however, cannot be well captured by using only the color information. Thus, we propose a new idea here and utilize CNN features together with RGB features in the Felsenswap and Puttenlocher framework to go from the Felsenswap segmentation to the deep Felsenswap segmentation. This also solves this under-segmentation errors that you can see in the top right, and solves these errors as is seen in the bottom right. The idea of the deep Felsenswap superpixel is that we want to integrate deep features into the distance computation in the Felsenswap superpixel segmentation. Originally, Felsenswap superpixel segmentation only takes for the distance in the feature space only the RGB features of adjacent pixels I and j, as we denoted here, with the Euclidean distance between the RGB vectors pi and pij. We want to add another term based on feature vectors as embedding vectors from deep features, fi and fj, and want to add the cosine distance here as well. How do we get those features? Well, first we design a lightweight encoder-decoder architecture with only 9 layers and combine features from different scales of these encoder-decoder architecture. Then we extract a per pixel feature for every pixel and use these features here as our fi and fj for each pixel. Hence, this tensor has the same resolution as the input image. How do we train those features? For this, we use an auxiliary task, the pixel affinity task, and force that the cosine distance between adjacent pixels within this tensor is 0 if the pixels belong to the same segment, or 1 if the pixels belong to different segments. And when doing inference, hence when only doing testing, we only need to extract this turquoise box here, these features, and integrate it into the distance computation as fi and fj. Hence, no further changes in the Felsensweib superpixel segmentation framework is necessary, as we keep all the properties of the Felsensweib algorithm. Subsequently, we use these deep Felsensweib segmentations to generate refined proposals. First of all, we present the general proposal framework. We start out from attention mask proposals. Attention mask is a state-of-the-art method for object proposal generation. As you can see in the top right, again, the proposals are not really precise. Thus, we add our deep Felsensweib superpixels here and also extract features from the backbone network of attention mask. Finally, we combine all the three outputs, the coarse proposals, the deep Felsensweib superpixels, and the extracted features in our superpixel refinement module and generate refined results based on classifying superpixels. We discuss the superpixel refinement module now in a bit more detail. We start from the three blocks, as you can see them here. In the red block, we have the coarse attention mask proposal, which is 10 by 10. We have in the yellow block the superpixel segmentation generated with our deep Felsensweib segmentation, and in the green block, you can see the deep features extracted from the backbone network. First, we upsample the coarse proposal, leading to a blurry variation of the proposal, which covers the entire image. Second, we apply superpixel average pooling on this upsampled result and generate something that we call mask prior. Thus, for every superpixel, we can now decide if it's rather foreground or rather background. The result looks roughly like this. This already is a lot more precise than it was before. In the next step, we apply superpixel pooling again, this time on the extracted features, and generate a feature vector per superpixel. Finally, we concatenate the mask prior and these feature vectors and forward this to a classification and classify each superpixel as either being part of the foreground, so the object, or part of the background. This way, we can generate our final refined object proposal, as you can see in the bottom now here. After briefly discussing our method, we want to show how our method performs compared to other state-of-the-art object proposal generation systems. We compare on the Elvis dataset, which has COCO images, but more precise annotations. This is very important for our evaluation since we want to precisely find the objects in this image. We compare based on the average recall, which is a standard measure for object proposal generation and measures how many objects are actually localized and how well they are localized. The average recall is usually denoted for the first 10, 100, or 1,000 proposals. We compare our method to four other methods on object proposal: deep mask, sharp mask, fast mask, and the attention mask. Note that our method is based on attention mask, however, refines those proposals. You can see in the numbers here that across all numbers of proposals, the average recall increases using our superpixel-based refinement. Especially for only 10 proposals, there is a large improvement. However, also for 100 and 1,000 proposals, there is an improvement. For 1,000 proposals, you can, for instance, also see that using the deep Felsensweib segmentation is better than using the classic Felsensweib segmentation, only based on color. Hence, our proposals locate more objects and locate these objects more precisely than the classic attention mask, fast mask, sharp mask, and deep mask algorithms. Additionally, using our deep Felsensweib segmentations is also beneficial for the overall results. Going into more details with how precise the proposal masks are, we also evaluate the best fitting proposal per annotated object by means of boundary recall and under segmentation error to standard segmentation evaluation metrics. You can see here in the numbers that the boundary recall is significantly higher for our proposals using Felsensweib or deep Felsensweib. Similarly, the under segmentation error is much lower for our methods. What does it actually mean? As you can see here in the top right corner, a low boundary recall and a high under segmentation error leads to masks that do not capture the object precisely. However, a higher boundary recall and lower under segmentation error leads to proposals that adhere better to object boundaries. Moving on, we present you our qualitative results. Here you can see in the left column the results of a tension mask for two images with multiple objects. You can see denoted by the red arrows several problematic areas of the proposal where the proposal does not precisely capture the object boundary. For instance, you can see here that on the leg of the tennis player, or between the legs, or here around the neck and the head area, that the mask roughly captures the object, but not precisely. Similarly, you can see here along the legs of the giraffe or the other giraffe, as well as around the head or the neck area, that similar artifacts are visible for the attention mask results. Comparing this to our refined proposals using Deep Felsenswalb, all those problems are essentially solved. Here you can see that the proposal fits very tightly to the object, here along the legs, between the legs, around the neck, around the head, and everywhere else. Similarly, for the giraffe, for both of the giraffes, you can see that the proposal also fits very tightly to the legs, the torso, the neck, and also the ears or the ossicones on the head of the giraffes. Some errors still appear. For instance, here a superpixel is wrongly classified as a foreground, although this is actually a stone and part of the background. We also compare the Felsenswalb to the Deep Felsenswalb superpixels in a simple segmentation framework, so without object proposals. You can see here in the left column the original Felsenswalb results for two images. And you can see here pretty well that there are several under-segmentation errors marked by the red areas. Here, for instance, the foreground color and the background color are very similarly here. So it's very hard to distinguish for classic Felsenswalb using only color that these are segments from two different objects. If we use our Deep Felsenswalb method with the CNN features, those problems are gone. So we can clearly distinguish here between the giraffe and the background, or here, for instance, between the elephant and the background as well. To sum up, we have discussed that most superpixel segmentation algorithms utilize only low-level features like color for generating superpixels. To improve that, we use CNN features and the Felsenswalb-Puttenlocher superpixel segmentation framework and generate better superpixels that are able to cope with more objects with texture or multiple colors. Second, we use these superpixels to improve the imprecise object proposals generated by modern CNN-based systems by combining the cross proposals with the precise superpixels and classify each superpixel as foreground or background. This leads to an improvement in the overall object proposal results, and specifically leads to a better boundary adherence of our object proposals, as you can see it again here on the right-hand side. Overall, we can say that superpixels and CNNs can be a very useful combination if you apply it in the right way. Thank you for your attention, and visit us in the NectarTrack session Room 3. Please check also out our paper and the code for our superpixel-based refinement.